Clint Mason, Kaizen Well Solutions. Thought I would put together a quick presentation talking about gas lift and moving to Gapple, and I see a lot of the same problems, same issues that crop up every time we go out to do this. And oil and gas companies, engineers, operators and stuff, a lot of times are jumping over some very critical steps, in my opinion, for success, and it is creating some difficulties and also reducing the potential opportunities that a lot of these companies are seeing. So let's burn into this. It's hopefully not going to be too long, but I imagine it's going to take about 20 minutes, 25 minutes to go through all these this conversation. So let's first of all talk about some gas lift basics. Gas lift is really designed for a specific well condition, liquid rates, and the resulting temperature of those liquid rates, because that liquid pulls the temperature up to the valves. Available injection pressure, current line pressure, bottom hole reservoir pressure. So you design it for a point in the well's history, and then you try to expand or add valves, do all sorts of different things to encompass that well as it changes, as it goes through these changes. But you can only do so much of that. You can't put a system in that's going to lift 1,000 barrels a day and then expect it to work really good at 100 barrels a day. It's just not really possible, no matter what anybody tells you. And adding more valves and doing this and doing that, it's not really the solution. So there's some basic things we need to understand about gas lift and what's going on there. So as time changes, any of the well conditions change, the valve performance, or the TROs, which is test rack opening pressure, will change. You reduce the temperatures or increase the temperatures. It's going to change the dome pressures. It's going to change how it opens and closes. You change any of the pressures in the tubing at that point, any pressures in the casing. All those things can have different impacts on when the valves actually respond. Probably one of the biggest things is, of course, liquid volumes are decreasing and temperatures are changing in that midpoint of the well, and usually you see a pretty wide swing in the opening test rack opening pressure of that valve because of that temperature change. So, briefly, we purchase pretty well all of our equipment from JMI in the United States. Their API Q1, they're committed to quality, the engineered products, 25 years in the business. It's not really all that important who you use, as long as you ensure that they're a high quality manufacturer. It costs a lot of money to put this equipment in, so you don't want to put stuff in that has less than, I would say, spectacular QC processes and quality. We also use Mana, one of our main mandrel suppliers, whether it's conventional or it's side pocket and all the other types. And this is important to make sure you understand what you're putting in hold, because a lot of the problems we find is from subpar equipment to manufacturer and quality standards. So what is a conventional valve and what does it look like? So a conventional valve is a valve that's going to be on the outside of the tubing. And it's just typically what we use when we're trying to either go into Gapple, or if we're going to run a plunger lift through it, because a plunger can run through a conventional valve. It can't run through a side pocket valve unless we build this large, like 90-inch long plunger, and it has a whole bunch of other issues on top of that. But basically what we have here is you've got this valve. Here is your dome you fill up with nitrogen, which then puts pressure on these bellows. These bellows respond to the outside pressure, which comes through here and pushes and either compresses these bellows or extends these bellows as pressures go up and down. And if this valve gets hotter or colder, of course, this nitrogen inside here is going to expand or contract, which is also going to change that pressure. Then you have pressure on the valve, the pressure that's pushing, that can kind of come through your check valve. It can be pushing up on the bottom side if it's open, so there is some impact on there. Most of the valves we use are not. This is showing a spring in there that's actually forcing the the seat closed, but usually it's just a differential check. So if there's any kind of backflow pressure, it'll push it up and set it and keep it closed. It's not spring loaded, but we can do springs. But that's basically what a conventional valve looks like. Take this little plug out at the top. That's how we charge it and get the internal pressure that we need based on our programming to reach the TROs when that when that valve is in the well at depth and in that environment. So conventional gas lift is run by rig. Okay, so that means that all of the equipment has got to go in with the rig. There's no wireline retrievable parts in here. So that system runs into the ground and it's set. And then basically what happens is the bottom hole pressure of the well is going to push the fluid up hole. Now initially the well is going to have all sorts of high bottom hole pressure, so it can push a fluid column way up in the well. So that's why you have upper valves. There's no point in having upper valves if you have no bottom hole pressure. Putting more valves in for low pressure does nothing, because the liquid doesn't get to the valves anyways. So that's why you have these valves staged, so as your pressures drop, as it goes deeper, the upper valves close. They require more bottom hole. They require more pressure to open in the casing, and as the liquid volume's dropping, the pressure's dropping. So then upper valves close, and it slowly stages down. And then we have this: gas is injected, goes through the valve, injects through a small orifice into the mandrel, which then gasifies the liquid column. If you're in true gas lift mode, you're just basically gasifying that column, foaming it up, allowing it to get to surface where the well's own pressure can kind of push it out and fill that bucket. If you're below the liquid volumes required for true gas lift, then you move into what's called deliquification, where we got to inject enough gas to basically get the tubing rate above critical. And true gas lift is not about being above critical rate, it's about gasifying the liquid. It's a GLR manipulation. Where once you move into deliquification, because you don't have enough liquid to foam to get to surface so it can be pushed out by the well, you need to replace that liquid with gas, and you need to come above critical velocity in order to sweep that liquid to surface. So typically when you're below, your liquid rates drop down below that point, you need to inject a lot more gas to get the same amount of fluid out. And so gas lift gets less efficient as it produces less and less liquid. So now side pockets, you're going to have like an orifice, a valve, a dummy, and all of these can be run and set in any side pocket mandrel. So you may have a dummy in this mandrel, and all a dummy is it's just a plug. There's no access, so it doesn't do anything. Then you'll have a valve which is set with your operating pressure, TROs, and then you might have an orifice, which is just a flow-through device that we put an orifice in there to control the amount of gas can possibly go through that. That's typically going to be landed at the lowest point of your string, or if you were really doing things properly with these side pockets, you'd be setting the orifice at your liquid level to get your maximum throughput, or maybe one mandrel below that, and then have the rest of it dummied off. And then over time, as your liquid level drops, you'll move your orifice farther and farther down the well, which is going to give you the highest throughput versus having a valve, which is going to allow you to pull that well down quicker and move it. That's kind of really how side pockets are supposed to work. A lot of people basically build a full system, like if you're doing a conventional, and then they go in and try to trip valves out and change it afterwards. It's 6 of one, half a dozen the other. I think actually the better process is to run a bunch of mandrels, run mostly dummies, set your orifice where your fluid levels, where you're going to get the best bang for your buck for injecting, because you can only inject so deep because you only have so much pressure at surface or whatever. So you set that orifice there. Once you get the level to drop because your bottom hole pressure is dropping, then you just keep staging it down, and then you start adding valves and doing all sorts of things from that point. So now setting a valve, side pocket valves are usually run and set by wireline. So basically they're always and you can see here I have a tool here with wire line, runs down, it gets kicked over, that valve then is pushed over to the pocket, it's hammered down and set in that pocket with a latch that unfortunately I'm not showing here, but that latch holds on. Then the tool shears off and leaves that valve there. If you want to recover it, it basically runs in, latches onto the latch with the same type of tool, kicks it over, tool kicks over, goes into the side pocket, latches the top of the valve, you jar it out, release it, and you can replace it. Hopefully, that's the theory. It doesn't always work that way. But here you can see that in that prior video, you could see that gas is being injected, going through the orifice or through the valve and into the tubing, lifting liquid. So it's important that you have the right setting for when you're running that. So mistakes producers make. Now that we've kind of given a brief overview of gas lift, the biggest mistakes we find is assuming that you can just throw a plunger lift in a conventional gas lift system and see success. Our experience has been, though, this is not typically the case. What we typically find is the Gapple systems are not operating properly because there's no reduction in gas injection volumes. And really, that's what should happen. If you need to inject enough gas to keep the well above critical to lift the liquid, we know we can lift that same amount of fluid, usually around 60% of critical, with a plunger lift. So if you're having to crank up more and put more and more and more gas into the well to make this system work, it's telling you something's wrong. It shouldn't be that way. On average, we find that probably, I'd say 60%, probably it's higher. It's probably closer to 80% of the wells we check with CO2 well tracer or echo meter, we find pretty significant issues from unidentified holes in the tubing to multiple serious failures. We do find a lot of orifices in the bottom, especially in the Montney up here, and we see that in the Duvernay a little bit, where we'll actually see the orifices plugged off. We'll see upper valves that are scaled off. And what happens is that forces, they become plugged, and of course then you start injecting higher and higher and higher in the well because the valves have to open or the valves become damaged above that, and it doesn't, because all the pressures have dropped. If you're still using your old data from your initial design, your surface injection pressure may be the same, even though you're injecting much higher than you think you are. So it's probably one of the biggest things we see is, and this is even after just a couple of years, we find a ton of plugged orifices and bottom, say 300 to 500 meters in the bottom of these wells where the scale is built up around the valve and plug them off. So some proper steps to be taken to ensure success. Confirm the gas lift valve operation is working, and I can't stress this enough, you can't do it by just looking at pressures. It means nothing. It means nothing at surface. You got to either go in with a gradient, do a flowing gradient to make sure they're all good. Maybe a dual mic echo meter might show that things are good. Probably not, but it's one of the things we do. Well tracer, CO2 injection guarantees it'll show you anywhere that there's gas going, and you'll be able to figure it out. But if you do take your pressure, you need to do a mass balance evaluation and ensure that what you think is happening is happening. If you don't do mass balance, we use wind glue. However, you're going to get that information. It means nothing by looking at pressure. You need to know how much you're injecting. What is the throughput at that? What you think is the point? I mean, there's a lot of times where people are injecting, 1 million standard cubic feet or 28.3 E3, and then if you look at the size of the throughput and the differential pressures, the maximum capacity going through that orifice is 7 E3, and then they're pumping 28 through, assuming that they're going down to that low point. Well, they're not. They're either multi-pointing, there's a hole, there's something washed out, something's going on. So you need to know all this information to ensure that you're injecting at the right point. Number 2 is ensure the tubing and the profile nipples are in the proper position. I always recommend end of tubing 70 degrees. You can go to about 75, but somewhere between 70 and 75 in my experience has always been the best. we've had the best results from. Nipple, 55 degrees. Sure, you can run a little deeper, but that's where you should be around, where you should land your bottom hole spring, around that 55, maybe 60 degrees, 45, somewhere in there. But the 55 should be a target. If you run a packer on off, it should be somewhere probably around 65 degrees. If you're in a vertical well, end of tubing should probably be midpoint of perfs, or at minimum right at the top of the perfs. Your profile nipple should be one joint above that end of tubing. And if we were just pour boring where we're coming around the tubing, that's the way to do it. If we're running a packer, then you'd have to leave space for a packer and an orifice. And so that might be 2 or 3 joints above the end of tubing by the time you fit all that in. The other thing is, when you switch from gas lift to Gapple, don't just go turn all your chemicals off and do all that. If you're using chemicals today for wax control, scale control, leave it running. Don't change anything. Get everything running smoothly. Make sure you got it operating properly. And then you turn this stuff down slowly over 3-4 weeks and ensure that you're not going to all of a sudden add to a bunch of problems. Because if you know the chemical's working, keep that out of the equation of why maybe your system's not working properly. Keep the chemical going. Then you turn it down, which you should be able to do. You might even get to the point where you don't need it at all. But don't get in a rush doing that. Very common issues we find: scale buildup on the orifice and lower valves. Unidentified problems. We'll find holes, lots of tubing in the bottom, 300-400 meters or 1,000 feet of wells. We see this in the Permian. We see this in the Montney and the Duvernay and stuff, where we get lots of corrosion and stuff, whether it's chlorides or I don't know, maybe it's just poor tubing. I'm not sure, but we find a lot of that. We find a lot of scale again in the orifice and lower valves, and it's packing right into the valves. So the scale definitely is coming in, and we actually notice that it seems to be worse on wells that have been flowed annually for up the annulus for a while, or maybe without tubing at all. And then when they start re-injecting, I think it sweeps a little bit of that down, and it slowly builds up in those areas. That's the plug valves, where we produced. Now here's what I was talking about: plug valves and scale buildup and crap that comes out of that casing. And then again, like I said, holes in the tubing. We see a lot of damage tubing. So Gapple basics. Gapple, or gas-assisted plunger lift, is when you set your plunger at or near the lowest point of injection, and you can operate your well like a plunger lift using the injection gas to assist the plunger. It's important to understand that. When you go to Gapple, you're running this well like a plunger lift well. You're cycling it. You're doing all the things you would do with a plunger. There's PAGL, which is plunger-assisted gas lift. In that, I operate it like it's a gas lift and plungers assisting it, so you would use different mindsets. Okay, so we're going to talk about Gapple, which is typically where most of these wells are going. You're landed as low as you can. You're landed just above the orifice. You're just cycling this well, whether you're using a conventional or a quick trip type plunger, free cycle, 2-piece, it doesn't matter, but that would be a Gapple application. Typically, the goal of Gapple is to reduce injection volumes and stabilize well production. If you are landed high in the tubing, because the lower, let's say you got 2 or 3 side pockets down lower, and you were just using plunger for mechanical dewaxing, this would again be classified as a PAGL, or plunger assisted gas lift, because now you still got to operate that well like a gas lift. You have to inject enough gas to get the liquid from where you're injecting up to the plunger. That may be at critical rate or above critical rate, or slightly above. Where Gapple, we can go below critical rate and still lift as much fluid. Again, with PAGL, you operate the well as a gas lift using plunger to assist you, typically for dewaxing purposes, might be one example. Usually people that are running PAGL, they're trying to reduce chemical dewaxing costs. There can be small production benefits, but typically you must, again, continue to inject and operate it like you would a gas lift. So beat that up enough, I think. A plunger is a plunger is a plunger. And the reason I bring this up is because the second people put a plunger lift system into a Gapple application, they start to believe there's some sort of black magic that happens. And it's not. If a plunger will come up, if that was a non-gas lift assisted well, and you put that plunger lift in and you're doing 14 E3 or 500,000 a day, and you know from experience and from the calculations that it can lift that plunger to surface if it was just a plunger lift. There's no reason why a Gapple well where you're injecting gas doesn't do the same thing. Nothing changes. If it's not coming up, there's something else going on, and it's not the plunger lift's fault. And everybody goes right to the plunger and say, oh, we got to pull the plunger up. Well, the first thing is, if you got to pull the plunger up, what does that tell you about where gas is being injected? It's not where you think it is. Okay, nothing to do with being sitting at 55 degrees or any of that stuff. It's all about understanding that it's where gas is going. Okay, and that's the number one mistake most operators are making. The plunger will run like a plunger runs. So again, if you got 500,000 and you're lifting 20 barrels of fluid, the plunger's coming up, right? You know it would work if it was a regular plunger lift well. If it's not working properly, or you're having to inject 1,000,000 of cubic feet of gas or 28 E3 into a well to get this plunger to come up, there's a problem. It's not the plunger, it's where the gas is going. When your well is producing a total tubing gas volume in excess of 60% of the critical, and the plunger is not servicing within the rules of plunger set times, let's say normally a plunger you would expect it to be up in 17 minutes or 15 minutes, and it's taking it 35 or 40 minutes. Why is that? Again, it probably has to do where the gas is being injected, which is probably above where the plunger is actually sitting. And again, remember, a plunger is a plunger is a plunger. They will operate in a Gapple well the same as they operate in a non-Gapple well, and should come to surface and should respond to the total tubing flow production as if it was just a regular well. So if there's anything out of line, there's something else that's probably happening. So plunger is not cycling or not servicing. You must, for example, you must pull up the bottom hole spring to make the plunger to cycle. There's either a hole or a valve issue, plugging, upper valve is probably might be open, might be a combination of all these. Almost guarantee your multi-point injection, because everybody is putting in so many valves and basically ensuring that there's multi-pointing. So you may only be getting 5% of the gas you're injecting under the plunger, and the rest of it is going through 2 or 3 valves above it. And so maybe that's another reason why the plunger doesn't move very quick. Maybe the well only produces 5 E3 or 6 E3. It's sitting there, there's almost no gas going by the plunger, but if it slowly moves up and gets to this next valve up, well, now all of a sudden there's 10 E3 going by it because you're injecting a bunch. Then the next one it goes by, it's at 14. The next one it goes by, it's seeing 20 E3 of gas. Well, then it's racing up the hole real fast, but it might take it 10 minutes to get to that point. And that's also when you see a lot of people start cranking up the injection, because they think if they keep cranking up the injection, the plunger should come out faster, which is probably what's going to happen. But if you think about it, the more gas you put in, the orifices in those valves can only let so much gas through. So pushing more gas in brings the pressure up and actually opens up valves higher and higher and higher. And really what it does is it doesn't make the plunger move any faster, not at least until it gets to the point where that extra gas you pushed in is injecting. So if it's halfway up the well, it might take it 20 minutes to get to that point, and then 2 minutes to get to surface, which is why we see a lot of damage in Gapple wells, is because people have cranked up the gas so high to get a faster run, not realizing that it's not faster until it gets past a point up high, and then that plunger comes in so hard, it's moving so fast that you start damaging things at surface. And so it's important to remember that injecting more does not result in better performance. And you got to walk away a little bit from this idea that you got to have the plunger up in 15 minutes or whatever the magic number is. Sometimes you got to accept that if we got a problem in the tubing and a bunch of the gas is being injected a little bit high, but the plunger is coming up every time, maybe you just got to accept that it's going to take 20 minutes and not 12, and don't keep cranking up the gas. In fact, you might want to try to reduce the gas, because if I inject less at, up here, it might move quicker from this point to this point, and so it might actually do a better job. So don't get stuck on this idea that you need to have a plunger up in 12 minutes or something, especially if we've identified there's an issue up hole. So some of the things, now we'll talk about well tracer because we use that a lot. The advantage of properly identifying the well condition, and it does pay back very quickly, is that as soon as we know where the gas is actually going, we can actually calculate velocities throughout the entire tubing string. And we know how long it's going to take to get from the bottom hole spring to that first valve, to the second valve, to the third valve. And then we can say, hey, look, it's going to take 30 minutes for that plunger to come up if you're injecting this because of where the gas is going, and accept it. Or you may believe, or may create a case where it justifies doing a rig workover, removing a bunch of those valves or redoing them. Probably if you're at the point of Gapple, you may only need 1 or 2 valves, or maybe you just need an orifice just below where the plunger is sitting, and because you can reduce so much gas injection, you might be able to cut your injection by 70-80%, or a lot of these wells practically no injection is required, if any, and we can make it go. So here's an example of a well we were looking at, and I don't care about the valves, these are good valves, so there's no problem here. But what was interesting is when we went through and looked at this well, this is a well tracer we did, we saw these big kicks. Now we assumed that this well was down at the orifice. That's what the pressure should have shown. That's whatever, if you would have just taken a snapshot of the casing pressure, and you could have said, hey, according to our design, we should be injecting at the orifice. But here's what we actually saw. Valve 4 had a huge return. Valve 7, Valve 8, Valve 9 had a return, but there's no returns after Valve 9. So 10, valve the 10 and the orifice, no returns, and we should have been at the orifice. So that really meant, when you look at this, probably the majority, 60-70% of the total injected gas is way up hole. So because of that, it didn't matter how much we injected, or if we were going to put a plunger into this well, it really would have done very little to bring that plunger up from the orifice. And as it turned out, when we were done and this well was pulled out, those bottom two, the orifice and the 10, were completely scaled off. Valve 4 was damaged. All these other valves were damaged because, or the well conditions had changed enough, and they were multi-pointing. Here's we've got some issues here. So valve 4 was damaged, allowing a significant amount of the injection gas to enter the tubing. 7, 8, and 9 are injecting, but ultimately the actual condition of the valves were not known until they were pulled out, likely injecting because there was some multi-pointing and temperature changes, and valve 10 was plugged and the orifice was plugged. So if we put a plunger lift in there, it would have done nothing. So and here's kind of an interesting thing. So if we looked at that particular well and we said minimum rate for, so I got a couple of things on here. One is this well likely operating at the minimum liquid volume for gas lift? And this well is likely operating at below the minimum liquid volume for gas lift and is into liquefaction mode. So that means we got to inject enough gas throughout the tube string to bring it above critical rate to make that liquid come to surface. So here's this red line here, and that's basically kind of a roughly what our critical rate would be through the tubing. And this is when we did our gas lift well tracer analysis, we knew how much gas was going at which point, and this is what the rate of gas was at any one of these points throughout the wellbore. So we're above critical rate to valve 4, we're above critical rate to valve 7, and then we drop below critical rate. So basically this well is in slug mode once we get below valve 7. So that's going to mean that the well is not performing very well. And then we say, okay, well, if we put a plunger lift in there, what would happen if we didn't change anything? Well, if we assume that the well's minimum rate for a continuous cycle plunger is 60%, we're just above, or sorry, we're just, here's what our requirement would be, this purple line. And this is actually what the formation gas is. And we know from valve 9, we're fully reliant on what the formation inflow is. And we're close, very close, you know, we're a little bit shy of what our calculation is. So there's a good chance that plunger would run, but it's going to move very slow from the orifice, bottom hole spring, until it gets to valve 9, and then it's going to move a little faster, and then it's just going to keep picking up speed. And you can see here, I mean, the total tubing gas rate was, you know, 1.07 MCF, you know, or 30 E3, but you know, the majority of it is way up the well, 6,000 feet versus where the orifice should be at 10,000 feet. So you can see how if we had a plunger in there, yeah, I could just keep cranking up that injection volume, but it would just push more up here. It wouldn't make that plunger move any faster from the orifice. You know, it might speed up a little bit here, but chances are 90% of the gas extra you inject is just going to go through these top couple of points. It's not going to speed the plunger up until it gets past that point. Then it's going to come very, very fast to surface and really start pounding the heck out of everything, damaging springs and plungers and stuff like that. So, potential injection gas reduction. Well, by fixing this well, removing all these issues, the potential injection gas rate reduction is about 620 MCF. It really only, you know, based on this, we only need probably 80 MCF to fall within that 60% of critical to run a continuous cycle plunger. You might need a little more, might need a little less, but that's roughly the opportunity. So there's that big of a reduction. Okay. So when is Gapple a good choice? I get asked this a lot. Well, when should we be looking at Gapple versus gas lift load? And again, I've talked a little bit about this. There's really kind of two stages. True gas lift, where you're above the minimum liquid volumes to keep the efficiency high, and it's GLR manipulation. And then deliquification mode, where you don't have enough liquid to foam to surface to get pushed into that bucket. And now you've got to replace that lack of liquid by high volumes of gas, and you basically got to go above critical to sweep the liquid to surface. So, and a lot of people don't really realize that there is some pretty high liquid rates when you drop below that efficient rate. So here, here's an example. So let's go 2 3/8. So our maximum liquid rate, and let's just give it a little bit of room here, but a good example is you're probably around 2,000 barrels a day is the maximum liquid you're going to push through 2 3/8 with gas lift. And when you start getting down to anywhere between 75 and 200 barrels a day, depending on pressures, you're starting to get into deliquification. Once you're below that volume, we need to start adding more and more gas to lift it. By putting Gapple in there, that reduces the amount of gas we need. Here's 2 7/8, you know, 2,500 maximum, 200 to 350 barrels per day, or 30 to 55 cubes per day. So, I mean, the majority of the wells we're running with gas lift today in these fields are probably in this range if they're 2 7/8, and could possibly be in the range if they're 2 3/8. So they need, you know, they're going to benefit from Gapple applications because that's going to allow you to continue to reduce how much gas you put in there. Now, if you got a 3.5 inch tubing, which some areas do, where the minimum liquid rate is 300 to 700 barrels per day, 50 to 120 E3 a day, it's in huge numbers where you are going to start seeing advantages from moving from gas lift to Gapple. So when Gapple is done correctly, we reduce gas injection, runs from the top of the orifice to the lowest injection point. It stabilizes production. Plunger should operate like a plunger, right? Should fit within those windows. If any of these things are not true in your well, it might require further investigation because there's probably a mechanical issue or a problem within your gas lift. Here's an example of a Montney formation, and we've done a whole bunch of these. just to show the impact. So this was steady state gas injection back here. Okay, this is over a 24-month period. These were big wells, great gas lift. We built the gas lift, we put it in, we know the whole history of this well. And you can see raw gas. Well's getting gassier, liquid is starting to drop. This is oil production up here dropping. Gas injection stayed very stable, started really having problems in here, and we're definitely below the rate and where we're being efficient with gas lift. We were definitely in the Gapple area. You can see they kicked up the gas, really didn't get much, continued to have problems lifting liquid. And then we came out there, we put a plunger lift in, started reducing injection volumes. That's what raw gas is, a combination of produced gas and injected gas. That's why you see that step down. It really didn't impact total produced gas, significantly reduced the injection gas, but look what it did to the oil production. As soon as we did that, we got, you know, something like a 25 to 35% increase in oil production. What was really interesting is we put this plunger in, and because you got gas lift, people kind of can tweak that gas injection to hide things like plunger wear and inefficiency. And you can see they were playing around with it. Then they started to increase gas, a little bit back in here. And they were like, we went out and looked at it. This was after 9 months, the first plunger we put in there. And that plunger was wore out, significantly undersized, so they were having to inject more and more gas to get the plunger to operate. And as soon as we put that brand new plunger in, they could reduce their gas way down again. It doesn't show, but yeah, it's down at this point here again. And another example why you should have, you know, I believe every 4 months you should do an inspection minimum, but at least every 6 months. This well would have benefited, you know, probably 4 or 5 months, 6 months. They should have replaced that plunger. It was operating good, the valves were good, everything's great, but it just, you know, the first plunger in that tubing, and it was a little rough, and it just wore that plunger out a little quicker than we would normally see. And that was what these issues indicated. And this is the difference between this is a good plunger and this is a wore out plunger, and this is, you know, back to a good plunger. How much it can impact how much gas you need to inject. Another example. So if Gapple is applied properly, the results are predictable. Good rule of thumb is you need 60% of wellhead critical rate to run a continuous plunger, like a 2-piece or our Pro Cycle, like a Dart style. And you should only need to inject enough to bring the total gas volume up to that 60% of wellhead critical. You shouldn't have to inject more than that. Startup and operations of a plunger. One of the big problems we'll see is guys will do things like hot oiling. It's typically not a good idea, and there's really no safe rate that you can pump liquid through a gas lift valve. It's pretty low, and before you're going to start damaging it. A lot of guys are hot oiling these valves or pumping hot water down, and basically they're damaging valves because they're pumping too fast, too aggressively. So it's something that you need to work on. It's better to deal with it with chemical and things like plungers or Pagel than a bunch of hot oil if you can. Understand that Gapple and gas lift are not the same. Gas lift is all about steady injection rates, maintaining constant flow of gas to lighten up the liquid fluid. Gapple is really in the unstable flow. You're cycling the well on and off, so the design between the two systems is quite different. We do design a Gapple system, if it's going to be Gapple, with significant differences in things like orifices, placement of valves, all that stuff. We do it quite a bit different because they operate differently. They have to operate differently, and we design them differently to maximize the production because of that. Review steps to 100% success. So here's something. Evaluate the well using good evaluation software like WindGlue, run echometer fluid checks, well tracer CO2 tests, redesign the gas lift according to the new well parameters and make sure things are right. Run oversized orifices sometimes below the bottom hole spring to improve throughput at that point. And we're not worried about casing heading at this point when we're in Gapple. We actually want to be able to get loss of volume through there. Make sure the inner tubing is at 70 degrees, nipple at 55, packer at 65. Some basic things that you can do to help improve that. Equipment quality does not come cheap. I'll say this. I see a lot of guys are, they're worried about a few dollars here and there, and there's a significant difference between a properly well-built valve, and which most North American manufactured valves are, and other valves that have a tendency to not meet the same level of I believe QC and stuff. I'm not picking on anybody in general, but I'm a big believer in North American equipment has better QC and stuff like that, but you have to work with somebody that you trust. Gas lift is very forgiving until you need it. This means anytime issues with the gas lift is not seen, and many times issues in the gas lift is not seen till months after it was installed, and the well has declined, and you can no longer push fluids effectively. You can cut the top valve out of a brand new gas lift system and not realize that you've damaged that system for several months, or until that well's production or pressures have dropped enough that it can't push liquid up to that valve, and then all of a sudden you just stop lifting liquid. And we've seen that happen too, and it's usually done in startup. Guys have damaged just being impatient, pushing liquids through too fast, all sorts of stuff. The startup is critical in protecting your gas lift. From the design, confirming well-bore and valve conditions, to setting expectations, startup, all these things, it has to be done properly by operation staff. They need to be trained properly, and we need to ensure that everybody is on the same page, because one piece of the big puzzle that gets a little bit impatient is going to damage this equipment or not run it properly, and all that money is wasted. So anyways, that's kind of the end of my thing. A little blurb from JMI and Mana, because we're a big supporter of their products, North American made. They're definitely a high quality manufacturer. We're not the only ones that use them. In the US, they're key manufacturers for a couple of good companies down there as well. Anytime you have any questions on that stuff, you're having problems, make sure you look at who's manufacturing your product. And just because the name is on there doesn't mean it was manufactured by that company. I've seen this, a lot of lower cost equipment swapped in and out of service in these bidding wars, where people are wondering, going to who they think is a company that builds great stuff, but in order to win bids, they're having to use, I would say, subpar or lower quality equipment, and it ends up biting the customer, the producer, in the end. So let's make sure, double check, set the expectations, and just remember, in Gapple, a plunger is a plunger is a plunger. It should run like a plunger. If it doesn't, there's something wrong, and it's likely not the plunger system. It's tubing, gas lift, valves, something is out of whack. You got a hole in it, and when people start dragging plungers up and down and moving bottom hole springs and that, they're not really solving the problem. They're just pulling it above the problem, and it's not giving you the best results. All right, hope this has been helpful. Have a great day, and talk to you soon. Clint Mason, Kaizen Well Solutions, www.kaizenws.com. Take care.